JPL is a NASA facility in La Cañada, Flint Ridge, California, here in Southern California, and our fundamental job is to build and launch spacecraft here on Earth and famously on other planets.
Woohoo!
Yeah.
So you grew up to have a good job.
I did.
So you are an atmospheric scientist.
Yes, I am.
Tell us about how you measure climate change from your perspective.
Well, our perspective, again, here at JPL is satellites, and our perspective is global. Satellites are necessarily global observations. They orbit the entire planet. And we live in an era of very advanced technology, obviously, and one of the things we get out of that technology is very detailed observations. So we have a detailed set of observations of the entire atmosphere, essentially.
And what is it telling you?
It's telling us, these satellite data sets provide information about how the atmosphere behaves and how it's changing slowly over time.
Okay, and so from a climate change risk perspective, I guess given the data that you've been accumulating here, what are the risks?
Well, the risks, this is, in some sense, my perspective as an atmospheric scientist who's slowly gotten into climate and its effects on, or humans' effects on climate, because I didn't start graduate school 25 years ago to learn about human effects on the climate. I just wanted to learn about the atmosphere. But one of the things we've learned is that humans have had a significant effect on climate. It's becoming very apparent, certainly in the last decade or two, that humans are affecting climate. My concern as an atmospheric scientist is that we don't fully understand how those changes will happen, and there's a chance that some of those changes will be actually quite minor, but there's also a chance that some of those changes will be very severe.
Okay.
And from a scientific perspective, you have to balance both those potential risks.
And I guess from a gambling, betting perspective, how do you weigh up those odds?
Well, I view myself as sort of a bookmaker or an odds maker. I'm trying to understand what's the most likely scenario to turn out and which are the extreme ones. And frankly, in this situation, the extreme events are very little change or very severe change, like rapid sea level change in a generation.
Okay.
And it's looking more and more that those extreme events, meaning very little change or rapid change, are roughly equally probable.
Okay, so either a whole lot of bad things or not so much in equal measure.
Equal measure.
And what about in the middle of that spectrum? What does that look like?
The most likely scenario, and this is the scientific consensus, is that there'll be slow changes in climate, slow shifts in climate regimes.
Okay.
Yeah.
So, why did you become a scientist?
I became a scientist because like most scientists, I wanted to understand how the natural world worked. And our atmosphere is part of the natural world.
And so now you find yourself in this sort of very important global debate
Yes.
from what sounds like a fairly mundane beginning, Eric. Atmospheric studies.
Just a little historic perspective. I remember once, I did my graduate work at the University of Colorado at the National Center for Atmospheric Research in Boulder. And I remember once having lunch with Stephen Schneider, the late Stephen Schneider, who ended up becoming a professor at Stanford. And Stephen was a very outspoken voice for taking climate and human climate effects seriously. And in 1985 or so, I remember him saying, oh, it's just a matter of time before carbon dioxide increase in the atmosphere becomes a major concern for everybody.
Wow.
And it took 25 years, but here we are today.
Here we are today.
Yeah.
Okay, and I guess the final question, just for an Australian audience, what is it about burning fossil fuels that causes this, increasing temperature? What is that link? How does the science work?
Remember, like it or not, when we burn fossil fuels, we produce large amounts of carbon dioxide. And carbon dioxide traps heat in the atmosphere, commonly called a greenhouse gas. It also paradoxically and somewhat unintuitively causes heat to be excluded from the upper parts of the atmosphere. So one of the signatures is that you're actually seeing cooling in the upper atmosphere at the same time we're seeing warming at the surface of the atmosphere. It all makes sense. It's all basic physics. It's the first thing you learn when you study atmospheric sciences. And so we're just playing with the system by creating lots of carbon dioxide.
Okie doke. Well, that doesn't sound too good. Thanks very much.
You're welcome very much.